Hi, everyone. My name is Kimoon. I'm a software engineer working for Pepper Data. At Pepper Data, we help people improve the performance of their big data clusters. That's our main focus. But we are also interested in exploring new big data platforms. In particular, Pepper Data and several other companies have been building a new big data stack on Kubernetes. So together, we made it possible to run Spark on Kubernetes. There was a talk on this topic yesterday. Now, we are adding HDFS, Hadoop Distributed File System, to the big data stack on Kubernetes. So I'm going to talk about that today. Here's the outline of the talk. First, I'll do a quick introduction on Kubernetes. Then I'll talk about how we run Spark and HDFS on Kubernetes. There's a short demo. And finally, we'll discuss some problems that we ran into. In particular, HDFS data locality was broken on Kubernetes. We fixed it. I'll explain how. But first, how many of you are familiar with Kubernetes? Raise your hands. Okay, a lot of people. Cool. All right, so what is Kubernetes? Kubernetes is a new open source cluster management software released by Google in 2014. So it manages many computers and runs many programs using those computers. In that sense, it is similar to Yarn or Mesos. What sets apart Kubernetes is that when it runs programs, it puts them in special runtime environments called Linux containers, which are better known as Dockers or Rockets. Containers and Dockers are super popular. People wanted to run them not only on a single computer, but on a cluster of computers. So Kubernetes does just that. It is actually designed and built for containers based on Google's experience of running containers internally for 10 years. Yes, Google has been doing that, right? So ever since it was released, a lot of people joined the project. Let me actually try this. And built a big community around it. Okay? So that's cool. I love Batman, but I'm not endorsing his violence here. Okay? But what's the benefit of using containers? Many of us have this bad experience, like my Spark job suddenly failed with class not found exceptions when someone installed a new version of Spark. Or I had to change my Tomcat port because someone else was running another Tomcat on the same host. They shouldn't touch my stuff, especially when it has been working fine, you would say. But what can you do? It keeps happening. Unless you use containers. Containers solve this problem fundamentally. They create more isolation layers between programs using virtualization technologies that virtual machines are based on. But unlike virtual machines, which are slow, containers are still very fast because they picked a specific set of technologies that are efficient and lightweight. First, each program gets a virtual file system that contains an independent set of software packages so that this other person can install new packages only on his container without affecting my program. What if I have a server program like Tomcat? Do I need to change the port depending on who else is running Tomcat, which sounds ridiculous? Kubernetes gives each program a virtual network interface that comes with a unique virtual IP address so that both my Tomcat and your Tomcat can open the same port under different IP addresses. And there are other technology as well. Right? This is like having virtual machines, a lot of them, such that each program is the only program running inside a given VM. So with this benefit of virtualization, Kubernetes became very popular among microservices, each of which is a simple server program that provides only one service. Okay, so here's how a Kubernetes cluster looks. We have multiple cluster nodes like node A, node B, and so on and so on. I'm showing only two for illustration purpose. Across the cluster nodes, we have multiple programs running in these things, pods. So what is a pod? A pod is a unit of scheduling and isolation in Kubernetes. So it runs a user program like Tomcat in a primary container. It also holds isolation layers like a virtual IP address in an infrastructure container that Kubernetes creates. So a pod typically consists of these two containers, but you can actually add more user program containers if you want. That's for like having sidekick programs, like copying data for your main program, Tomcat. Okay? So here we see pod 1, 2, 3. Each pod gets a unique virtual IP address, like 10.0.0.2 here. And notice these virtual IP addresses look very different from physical IP addresses of cluster nodes, like 196.0.0.5 here. This becomes important later when we look at Spark and HDFS together. Okay? All right. Okay, so some of us at Pepper Data looked at Kubernetes and thought, wow, it would be really great if we can run big data applications like Spark also on Kubernetes. Then we found that we are not alone. Engineers from other companies were thinking about the same thing, and they have started this GitHub project, Apache Spark on KNS already. So we joined the project and combined our efforts. Together, we modified the source code. Oh, by the way, this GitHub project contains a fork of the upstream Spark code, right? So together, we modified the source code of the Spark driver and executor so that it's possible to run Spark jobs natively on Kubernetes. Again, there was a talk on this topic yesterday. All right? Here's how it looks when you run Spark jobs on Kubernetes. You would submit your job from outside the cluster using a client, right? Your driver launches in a pod, and then the driver will have multiple executors launched across the cluster nodes. They also run in pods. Then driver and executors will get unique virtual IP addresses like 10.0.0.2 for driver, and then communicate with each other using these virtual IP addresses. And if other people run their jobs, that will create their own pods, and these will not affect your job. That's the idea. Cool, so that covers Spark, but oftentimes Spark stores its data on HDFS and reads and writes HDFS data while jobs are running. So how can Spark on Kubernetes access HDFS data if all we have is just Spark? Doesn't make sense. So we thought, what if we also run HDFS on Kubernetes? We have done just that recently. So HDFS has two types of daemon programs. The name node daemon runs on a central cluster node and maintains the file system metadata, like which directories have which files and where are those file data, right? And the data node daemons run on every cluster node and store the file data on local disks. So to stand up HDFS on Kubernetes, we need to run those daemons. Here's how we did it. First, we launched the name node on a designated cluster node, usually the first cluster node, and it stores the file system metadata on the local disk. Then we launched the data node daemons such that there's one instance of data node on every cluster node. They store the file data on local disks. These daemons still run in pods, but they are special pods. Daemons don't actually need virtual IP addresses that we talked about because there's only one instance of each type on a given cluster node, right? And they provide a single service, single global service that's used by all HDFS clients, including multiple Spark jobs. So there is no need to worry about the port collision. So we chose not to get the virtual network interfaces, which is possible. So they communicate with each other and HDFS clients using physical network interfaces of cluster nodes. So they are associated with the physical cluster node IP address, like 196.0.0.5. Make sense? And HDFS clients need to specify the name node address in their configuration files. So we registered a symbolic DNS entry for the name node and used that in the configuration file. Okay, so far, this HDFS setup is actually not very different from that of Yarn or Mesos. All right, okay. So without further ado, let's see them in action, demo time. Okay, this is a recorded demo in the interest of time. So first, I'm going to prepare the cluster a little bit. We got tiny Kubernetes cluster on AWS EC2, 3 nodes, 1 master. And we want the name node daemon to launch on the first cluster node. So I'm using a Kubernetes node label to designate the first node for this purpose. And we want the data node daemons to launch everywhere except the master. So I'm using, again, Kubernetes node label to exclude the master. This is just a preparation. Now we're going to launch HDFS daemons. So this part happens inside this, okay, what is going on? Network lag. Hopefully, fingers crossed. Okay, let me double try. Okay, that's better. So this part happens inside this public GitHub repo. Anybody can access it. So the repo basically has a bunch of Kubernetes configuration files for the name node and data node. And the first part, which just happened, is just a workaround for the Kubernetes bug, not very important. So here, we just launched the name node using this command line. The last command line argument points to the Kubernetes config file, and we are using this Helen launcher that allows us to override some of the parameters in the command line. Okay? So we just check if the name node is up, it's been created, and we're launching the data node using similar command line. And we're checking data node here, it's been created. So we have 3 data node daemons, data node pods, because we have 3 cluster nodes, 1 for each. Okay? Now they are all up. We're checking if the data node Java processes have reported to the name node. This is the name node view of the data nodes. All 3 of them have reported. And DFS is empty. I'm sorry. Okay, because we just created one. All right? Now we're going to run a Spark job using this HDFS. So this is going to use the familiar Spark submit command with this TerraGen Java code. So it's going to produce 10 gigabytes of data on HDFS. And this part is the Spark client configuration. Oops. Okay. So it just started. And so this is going to launch the driver pod soon and then go on for a while. So I'm going to pause this and fast forward to the end. Okay, this is a different console window. First, we're going to check if the data node and executor pods are launched. So the Spark-TerraGen-timestamp is the driver. Exec 1, 2, 3 are executor pods. They are all running. And we're going to take a look at the driver log inside the driver pod. So you see that executors have registered like this. And we also see tasks are being dispatched like this. And let's jump to the end here. Okay, the job just finished. All right, now we're going to check if this Trojan job actually created HDFS data using Hadoop ls command. Okay, the files are there. And we're going to check if data nodes have filled up disks. Previously it was 0%. Now is 25%. Okay, it's not lying. All right. Okay, coming back to the presentation. All right, so we just saw HDFS running fine on Kubernetes, and it can be used by Spark jobs. So are we done in terms of making this usable? The answer was unfortunately no. There was something really strange in this picture. So one of the key reasons why people use HDFS is because it's faster than other distributed storage systems. And it's fast in part because it supports this thing, data locality. The basic idea is that you should read your data from local disks whenever it's possible, because reading data over the network like this is slow. If your network is slow, which is often the case, so reading like this is slow, reading straight from your local disks is fast, right? So this data locality is mainly implemented in HDFS daemons, but it is also integrated with application frameworks like Spark. In other words, the Spark driver has source code that interacts with this data locality. When using HDFS, the driver can send tasks to particular executors that have the task's HDFS data on local disks. Magic word. What does it mean, right? Let's take a look at an example. This example is on Yarn, by the way, not on Kubernetes. Okay? So let's say this Spark job wants to read /file A and /file B on HDFS. Okay? As human, we see file A is on node A and file B on node B. We also see executor 1 is running on node A and executor 2 on node B. So we want the driver to be smart enough to send the task for reading file A to executor 1 and send another task for reading file B to executor 2. Then these tasks will go there. They will read data from local disks with the help of local data node daemons. Tasks will run faster. The job will finish earlier. Everybody will be happy. But the driver is not human. The question is, how does it programmatically knows that this is the right thing to do? There's a source code for that, and it is actually quite simple. The driver starts by, starts by asking the name node which data node is in charge of file A. The name node will say that's data node 1, and the associated IP address is this, 196.0.0.5. Basically, the IP address of the host that the data node 1 is running on, which is node A. Then the driver will do the second part. It will find the IP address of the host that executor 1 is running on, and that's the same 196.0.0.5. So both sides match, and the driver says, okay, file A and executor 1 are on the same host. So it learns that I can send the task for file A to executor 1 to benefit from data locality, right? Same story for file B and executor 2. So this code works just fine in Yarn or in Mesos. Now let's look at Kubernetes. This example is now on Kubernetes. Notice again that these executor pods get unique virtual IP addresses like 10.0.0.3. Okay? Let's look at what the code will do. The same driver code will not work here, right? The left-hand side remains the same, but the right-hand side is broken now because when the driver finds the IP address of the host that executor 1 is running on, it will now find virtual pod IP address 10.0.0.3. This will not match data node 1's IP address. In fact, this will not match any data node IP addresses. It's unique, right? So the driver will be confused. It would not know what to do. And in that case, it falls back to this DOM code and sends tasks to randomly picked executors. So it's very possible that the driver ends up sending tasks to wrong executors like this. Tasks will go there. They will read data over the network. They will be slow. The job will be slow. Here, we see only 2 cluster nodes. So there's a 50-50 chance of the driver making a wrong choice. Not too bad. But imagine a 100-node cluster. The driver will almost always make a wrong choice. We had to fix this code. The fix itself is not that difficult, right? Don't stop after getting the executor pod IP address. Also ask the Kubernetes master to find the cluster node that this executor pod is running on. There is an API for that, and get the cluster node IP address and compare that with the data node IP addresses. Let's see how the fix will work. Okay, so the left-hand side, again, remains the same. On the right-hand side, we map executor 1 to the pod IP address, and then map the pod to the cluster node and its IP address. Both sides match again. The driver will do the right thing. The job will be fast again. Everybody will be happy. Okay? So we fixed the code. The question is, does it make a difference? Let's take a look at an experiment. Here, we ran the same Spark job twice. First time without the data locality fix. Second time with the data locality fix. Okay? The job was Terra validate, which reads the output of Terra sort stored on HDFS and checks if all data items are actually sorted. All right? The 2 runs were processing the same input data, same size, same content. The size was 500 gigabytes, and we were using a Kubernetes cluster with 9 EC2 nodes. Okay? So looking at the duration of the 2 runs, it's very clear that the second run with the data locality fix finished much earlier, 10 minutes versus 25 minutes. Okay, so data locality fix made a difference. It made the same job run faster, more than twice actually. Pretty good. So here we're looking at a AWS CloudWatch chart, and there are 2 lines in this chart. The blue line at the top is disk read bytes per unit time. The orange line is network usage bytes per unit time. All right. Looking at the height of these disk read lines, it's very clear the second run read a lot more disk data per unit time, while its network usage was really low. This is because almost all HDFS reads became local disk reads thanks to the data locality fix. Compared with that, the first run has more network usage. This is because the majority of HDFS reads became remote reads because the driver sent tasks to wrong executors. And the network was slower than disks in this cluster, so this read is mostly remote read. The remote read can be only as fast as slow network, right? So that's why you see this disk read line and network usage line for the first run go hand in hand like this, because the slow network was holding back remote disk read all the time. And that's why the job became slower, the run became slower. All right, so I gave you guys plenty of explanation of why it's like this, but it's always better to have direct evidences. So, okay. This is the same 2 runs on Pepper Data product cluster analyzer chart. and we have HDFS local read chart, HDFS remote read chart. It's super clear. The second run had a lot more HDFS local read. The first run had a lot more remote read. There was a tiny bit of remote read in the second run. This happens when all the write executors are busy at the moment doing other tasks, and the driver was forced to send the task somewhere else to make a progress. Okay, so that's all I have today. To recap, we got HDFS up and running on Kubernetes. Basic data locality works, but this is still work in progress with these known problems. Even for the data locality line, we have some remaining work items, and we're working on them. If you're interested, please join us. This is an open source project after all. Thank you.
I think we have 5 minutes for Q&A. There and
okay. Hey, I asked this yesterday, and they said you are the best person to ask. Do you see any network performance differences between the different network interface backends?
Oh,
which is the best and which is the worst, etc.
So that's a good question. So we were actually wondering about that ourselves, but we didn't do any concrete experiments around it. So for this particular experiment, we obviously used the AWS EC2 cluster, and it can actually support multiple network providers. We're talking about Kubernetes virtual network providers here. And for this particular experiment, we used the standard Kubernetes network provider, right? But again, this is just an experiment focused on the validation of the data locality fix. But in the future, we are actually planning to do other angles of experiment, like comparing Yarn HDFS performance versus Kubernetes HDFS performance, like that.
Any?
Hey, I'm Karthik from Cloudera. Nice talk. It's very useful. A couple of questions. One is...
Can you speak louder, please?
Can you hear me now?
Yeah.
Okay. Couple of questions. One is, I know you're querying the Kubernetes master for the mapping between the executor and the node. What's the latency of that? How many calls can Kubernetes master tolerate, like the throughput and stuff like that?
So getting that information, right, mapping from pods to the cluster nodes actually happens asynchronously in a background thread. So obviously there's some latency, but latency, in my opinion, didn't matter that much because when the driver asks this question, the information is already there.
Okay, cool. Yeah. The other question is, say someone's running a 1,000-node HDFS cluster,
yeah,
right? But when they run Spark jobs, maybe they only care about, say, like 100 executors, right?
Right.
I understand that you would map the data as close as possible based on the executor, but have you guys looked at all about executor placement in the first place?
I'm actually glad that you asked the question here. So that's actually this remaining work item, node preference.
Oh, okay.
Right? You got the right example. Okay. You have a 1,000-node cluster, but your data is pretty small, right? It's residing only on 10 nodes. So we're actually working on that right now. I wrote a pull request like last week for handling this. So Kubernetes has this mechanism called node selection and node affinity. So you can actually get the list of those cluster nodes that have your data and ask the scheduler, can you, schedule my pods, right, on these nodes if possible. Otherwise, I'll be fine, but please, right? So we are working on that.
Thank you.
Yep.
Hey, this may be a
this
may be a basic question.
Where is the person asking question? I'm blinded by it. Okay, great.
Yeah, this may be a basic question. It's pretty clear, running Spark on Kubernetes is quite useful. It's also, this is a lot of work, so I appreciate it. But, you have actually pinned HDFS to those nodes. It doesn't seem like what's the point of doing all of this work here?
So are you asking about HDFS running outside Kubernetes cluster?
Yeah, I mean,
Right. So that's a very good question. So the first of all, a related question is, can Spark on Kubernetes access, right, off-cluster HDFS that's running together with Yarn or Mesos, right? The answer is definitely, and we actually have tested it, and so it just works fine. You just need to specify the name node address of the off, cluster HDFS, and it just works. The point of trying to put HDFS inside Kubernetes is basically getting the best performance out, right? So if you're running HDFS cluster outside your Kubernetes cluster, by definition, you will not get any benefit of the data locality.
Yeah, no, that's not really
Right.
the.
But I understand that performance is not everything, right? Every time. So we actually recommend and encourage people to start using Spark on Kubernetes, right? Using some HDFS outside the Kubernetes cluster. This is just for laying out the groundwork for future, right, big data stack where you might want to move everything to Kubernetes. Make sense? Maybe if there's more, I can talk about
Yeah.
Yeah.
Probably, so guys, big round of applause for Kimoon.
Thank you.